a great pleasure and a great honor to be here. It's my fourth time in China, every time I've been to Beijing. And it's a pleasure every time enjoying the culture and everything here. I'm going to talk a little bit about the history of deep learning, but a little bit about the state of the art, and quite a lot about the obstacles that we are encountering in making progress towards AI. And hopefully inspire some of you to work on those problems, which I think are the ones that separate us from the current state of the art and truly intelligent machines in the future. If you could please switch in the slides. All right, wonderful. This is a beautiful Facebook AI research logo, which I'm going to switch. So yes, this is my name in Chinese. Many years ago, in 2009, I came here to teach at a summer school at Peking University, and my wife and I went to the summer palace, and we encountered a calligrapher. I asked him to write my name in Chinese. So I don't know if this is accurate. Maybe you have a better idea of how to translate your name to Chinese. Okay, so I know this is a very diverse audience, and I'm going to try to kind of give an idea of some state-of-the-art in progress in AI that will appeal to both people who don't know much about AI, who are more interested in the kind of the technology and market side of things, as well as to people who are kind of more into the research side of AI. And I know a lot of you here are very much involved in this. So let me start by explaining the basic principle of machine learning that almost all of the current applications of AI use. And it's called supervised learning. So supervised learning is a process by which you show a bunch of examples to the machine, and for each example you tell it what the correct answer is. So for example, you want to train a machine to distinguish images of cars from images of airplanes. You show it thousands of examples of a car and thousands of examples of airplanes, and you'd like the machine to turn on the red light when it sees a car and to turn on the green light when it sees an airplane. And basically you can see the machine as a black box with lots of knobs on it. And every time you show an example of a car, you tune the knobs just a little bit so that the brightness of the red light goes up and the brightness of the green light goes down. And every time you show an example of an airplane, you adjust the knobs so that the brightness of the green light goes up and the brightness of the red light goes down. And that's supervised learning. So basically, in kind of slightly more mathematical terms, what you're doing is that you're measuring the difference between the output you want and the output that the machine produces, and then you adjust all the parameters in the system that determine the input-output function of the machine in such a way that the output you get is closer to the output you want. That's supervised learning. It's a bit like showing a picture book to a small child. You open the book, there is a picture of an elephant, you tell the child that's an elephant. And after a few examples of each of the animals, the child can recognize it. So the difference with a child is, in the case of deep learning, you have to show thousands of examples of each category before the machine can perform well. But if you show sufficiently many examples and if the machine is sufficiently complex, it will essentially develop the appropriate internal representation of the world that will allow it to distinguish any car from any airplane, or any chair from any table, or any other object. So that's the idea of supervised learning. And almost all of the applications of machine learning and deep learning that you see today are the result of supervised learning. And the history of supervised learning goes back a long time ago, the late 50s, when a gentleman by the name of Frank Rosenblatt at Cornell University developed a machine called the perceptron. The perceptron was actually a physical machine. It was not a programmable computer. It was actually a physical analog computer that was built. And it basically created a model of pattern recognition that has stayed with us since that time until fairly recently. So the basic model of pattern recognition is you take let's say, an image or a signal, whatever it is, and then there is some sort of handcrafted feature extractor that turns the raw signal into a vector of features that indicate the presence or absence of a particular motif on the input, if you want. And that generally has to be designed by hand. It's kind of the module that you see in the middle here in the photo, which is sort of a spaghetti plate of mini wires. And then you have a relatively simple trainable classifier. In the case of the perceptron, it was what's called a linear classifier. Basically, it computes a weighted sum of the components of the vector, and if the weighted sum is larger than the threshold, then it's category 1. If it's smaller than the threshold, then it's not category 1. So what was new in the perceptron is a learning algorithm that allowed to adjust those coefficients in this weighted sum. But that model, in the last few years, because of deep learning, has been replaced by a slightly more general model, pictured at the bottom here, where basically a deep learning system now, instead of being composed of a single handcrafted module followed by a trainable classifier, is basically a cascade of multiple modules, all of which are trainable. Okay, so that's why it's called deep learning, is because those systems are composed of multiple layers, and all of them are trainable end to end. And it's a very old idea, really. People in the 60s had the idea that this was a good thing to do. They just didn't have the good learning algorithm for it. And then people in the mid-80s also came up with what's called now the backpropagation algorithm, which I'll explain in a minute, that allows to adjust the parameters in those systems. But it wasn't really very successful until recently, when we started having lots of data, very powerful computers, and slightly better algorithms than in the past. But there was some success back in the 1980s and 1990s. So how are those things built when we build a deep learning system? Basically, it's deceptively simple. A deep learning system is a succession of alternated functions that are themselves very, very simple. Essentially, you represent the input as a vector. So for example, the pixels of an image, you can think of them as a vector of values, or the values that represent a speech signal or a text. And the first operation you do is you multiply this vector by a matrix. Okay, so it's very simple. It's essentially you're computing weighted sums, or dot products. And the result of multiplying this vector by a matrix gives you another vector. And you take each component of this vector and you pass it through a pointwise nonlinearity, which is represented on the top right. It's called, in the kind of language of neural nets, it's called a ReLU, which means a rectified linear unit. What it does really is that it takes its argument, and if the argument is positive, it just copies it on the output. If it's negative, the output is 0. Very simple. It's halfway of rectification, okay, positive part. So by alternating matrix multiplication with this pointwise nonlinearity and repeating the process multiple times, you can show that with only 2 layers of that, you can approximate any function as close as you want. And what turns out to be surprising for some people is that by stacking multiple layers of those, there's a lot of functions that can be easily represented with a relatively small number of those elements, if you want. So the coefficients in the matrices are the ones that are going to be adjusted by the learning algorithm, because it's those coefficients that determine the input-output function of the neural net. And that's done through gradient descent. And so the first thing we have to do is compute the gradient of some objective function that measures the discrepancy between the output we want and the output we get. Here it's denoted C. And so it measures the distance between the output we want, Y, and the output we get out of the system, the output of the last module in the chain, if you want. And what we need to do is compute in which direction and by how much to change all the knobs, so all the coefficients in all the matrices in such a way that the error goes down. And that turns out to be very easy to do. It's basically a practical application of a very sophisticated concept in mathematics called chain rule that has been with us since the early days of calculus. Newton and Leibniz basically invented it. So it's not particularly sophisticated, and it's all the math there is, really, to understanding backprop. So essentially the idea of chain rule is if you have some idea of how the output of a module, so let's take the module I in the system, fi of xi minus 1 wi. So xi minus 1 is the input to that module, fi of xi minus 1 wi, which I denote xi, is the output of that module, and wi are the coefficients in the matrix within that module if you want. So if you know how each output of this module influences the cost function, the objective function, which is the gradient of the cost function with respect to xi, denoted dc over dxi, then, which is here, then by multiplying this vector by the Jacobian matrix of this box, you can get this other vector, which is now the gradient of the cost function with respect to the input to this module. And the Jacobian matrix of this box is basically a matrix that each entry indicates how much the output, a particular output is influenced when you modify a particular input by some small factor, essentially. And you can do the same with respect to the parameters. So by propagating signals backwards with this chain of modules, and then computing the gradient with respect to the parameters, what you get is the gradient of the objective function with respect to every single parameter in the system, and you can just take a step in the negative gradient to kind of lower the error. So that's a very short, quick description of deep learning, and it's really all there is to it. And so it's kind of a slightly more sophisticated form of curve fitting, really. It's nothing more than curve fitting. I know a lot of you here have backgrounds in economics, and so you certainly learned how you fit a line to a bunch of points. That's basically how to fit a complex function to a bunch of points. That's what it is. So a particular form of neural nets that's been very successful is convolutional nets. And this is a model that I started working on and kind of developed when I was at Berlitz in the 1980s. And it's inspired by neuroscience, really. So it's based on the idea that instead of having a full matrix, that you instead of viewing the input as a vector and the weights of the layer as a matrix, you view the input as an image. Let's say if it's an image. And then the matrix is actually going to be sparse, and it's going to have some structure in it, and it's going to correspond to what's called a convolution operation, hence the name convolutional networks. So what are the convolutions? So you take an image, you take a patch on the image, and you compute the dot product of the pixels within this patch with the weights, which is called a convolution kernel. And the result of this dot product is going to give you the pixel in this feature map here, which you're going to pass with a nonlinear function. And then you do the same with the same weights all over the image. So you slide this little window all over the image, and for each location of the window, you get an output pixel. Okay? And you can do this with different filters. So the coefficients of this filter are going to be learned. And we're going to have multiple such filters per layer. So here, for example, we have 4 filters, each of which gives a different feature map. So you can think of each of those filters as detecting a particular motif at every location in the image. And because of that propagation, we're going to learn those coefficients of those filters. Then there is another operation called pooling, whose purpose is to eliminate a little bit of positional information about where the features exactly appear. I'm going to show this in more detail later. But for now, suffice to say that it reduces the resolution of the representation. And then we repeat the process. So the next layer up, each feature map here is a result of applying a filter to every single feature map on the previous layer, adding up the results, and passing it with nonlinearity, and then there is another layer of pooling, and then more convolutions, etc. You can stack many layers of those. And this is the architecture here is very much inspired by classic work in neuroscience, in computational neuroscience, from the 60s. In fact, this is so famous that it's Nobel Prize winning by Hugo and Wiesel in the 50s and 60s, who analyzed the structure of the visual cortex in cats and various other animals, and figured out that there was this idea of sort of local connections with feature detectors that were replicated across the entire visual field. And there was this notion of pooling that they call complex cells. So here's an example. This is an old convolutional net from the 90s that we trained to recognize handwritten digits. And what you see here is the result of this pooling operation. So we take the first feature map of the first layer here. So this is the input, this is the first layer with 6 feature maps, and this is the result of pooling, the pooling operation on this feature map. It basically computes an average or a max. I mean, in modern days it would be a max, but in this example it's an average of 4x4 pixel, 2x2 pixel neighborhoods, and then passes it through a nonlinearity after multiplying it by a coefficient and adding a bias. And so it reduces the resolution, which means that if this image shifts by 2 pixels, this one will shift by 1 pixel, and this one will shift by 1/2 pixel. And so basically you get a bit of shift and distortion invariance by using those pooling operations. And as you go up the layers, you get units that are influenced by a larger and larger portion of the image. So each of those units here is, it's not really clear what they represent, but each of them is influenced by essentially a 32 by 32 pixel square on the input. And each column is influenced by a different 32 by 32 window of the input. So it allowed us to do things like recognize characters, but also we quickly realized it allowed us to do things like recognize multiple characters at once. So we can feed the network with a combination of characters, and it's able to pull out the correct interpretation without having to do explicit segmentation beforehand. And that was kind of a big progress. This is a short video that demonstrates the system back in 1990, 92 roughly. This is my phone number at Bell Labs. It doesn't work anymore. And I hit a key, and there is a video camera that grabs the image, and then it sends the result to a special board, the DSP32. It's a digital signal processor. It was capable of the incredible speed of 20 megaflops. And that was the only way we could run this at decent speed. And this thing, was able to recognize very unusual characters and all kinds of weird styles, pretty early on. So that was really a big progress for the time. So this is a younger version of myself. This is Donnie Henderson, one of the research engineers in the lab, and Rich Howard, who was the lab director. So eventually that allowed us to build entire character recognition systems that we used to read checks. This was deployed in the mid-90s, around 1996, 1995. It was used in many banks in the US and Europe for ATM machines, for machines that read checks automatically. It was a fairly complex system that had a combination of convolutional nets, heuristic segmentation systems, as well as training at the sequence level in the loop. So that integrated kind of a language model, if you want, as well as some sort of Markov model type system. Actually, it's closer to what we now call the CRF, conditional random field. And this was able to recognize about half of the checks with less than 1% error, which was actually sufficient for commercial applications. So in our lab at Bell Labs at the time, there were kind of two camps, if you want. Within two offices of each other were invented convolutional nets and support vector machines within 2 years of each other. So one of my office neighbors was Vladimir Vatnik, who you see here. This was a department head, Larry Jacob, and this is a longtime collaborator of mine called Leon Moutou, who's now at Facebook. And Vladimir Vatnik did not believe in neural nets. He thought machine learning method should be well understood theoretically, and so he proposed this method called supervector machines or kernel machines, which have been extremely successful for a lot of applications. And Larry was head of the lab, and we had both the neural net people and the supervector machine people, and so he decided to have a bet. And so Larry Jacob bet one fancy dinner that by March 14, 2000, this was written in 1995, that by March 14, 2000, people will understand quantitatively why big neural nets working on large databases are not so bad. Okay? So they worked experimentally. It wasn't clearly understood theoretically why they worked. And so he basically wanted to challenge Valley to kind of explain why they work. That league bets one fancy dinner that Jackal is wrong. But if that league figures out the bounds and condition, that league still wins the bet. Okay, so this was really an incentive by Larry to tell that league to work on the theoretical issue. And so in 2000, it turns out Larry Jackal lost, because no one had actually proved why neural nets actually work so well. In fact, it's still the case. We still haven't figured out theoretically. We were just talking about this with Professor Yao earlier, that we don't have good theoretical justification for why neural net works so well. And maybe it's a good challenge for some of you to work on this question. But there was a second bet. The second bet is that big bet, one fancy dinner, that by March 14, 2005, no one in his right mind will use neural nets that are essentially like those used in 1995. And Jackal bets one fancy dinner that league is wrong. And Jackal won that one. In 2005, people were still using neural nets. And so this is a picture taken at the fancy dinner in 2005, where they shared the bill because both of them lost, or both of them won. So what's happened over the last few years is that convolutional nets have been developed very heavily, and what sort of made them work all of a sudden was the availability of large data sets for speech recognition and image recognition. So in the case of image recognition, the watershed was the ImageNet data set that had 1 million samples and 1,000 categories. That turns out to be a regime in which neural nets work really well. And what's happened is that there's been a mutation in the number of layers. So you have neural nets that have anywhere between 1 and 10 billion connections, sometimes even more, trained on, they have between 10 million and 1 billion parameters sometimes. Sometimes they have 20 layers, sometimes the more recent ones even have 100 layers. And so there's been kind of a growth in the size of those neural nets, and that's been enabled by the availability of graphical processing units, GPUs, that are capable of several teraflops per second. So why is it conceptually that deep architectures are so good? And it's because the point of deep learning is not just to classify, but it's to represent the world, represent the perceptual world, the visual world in the case of image recognition. And so what you see here is a visualization that was produced by my colleague Bart Fergus with his student Matt Ziller a few years ago, that shows which type of features or motif are detected by feature detectors at various levels in the convolutional net. This is actually a fairly deep convolutional net with something like 15 layers or so. And this is the features detected at the first layer, so that's an indication for local motifs on the image that will maximally activate a particular unit in the network at the first layer. That's a couple layers up. You start to see detectors that can detect simple motifs like ratings, corners, circles, and things of that type. And then a couple more layers up in the chain, you see detectors that can detect sort of fairly complex parts of objects. And you have to ask the question, why is it that it's advantageous to represent the world this way? And the perceptual world. And the reason possibly is because the world is compositional. So physicists know very well that we can reduce objects to molecules, and molecules to atoms, and atoms to elementary particles, superstrings, whatever. Right? So essentially, a small number of distinguishable parts can be assembled in lots of different ways to form complex objects. And the perceptual world is similar. So an image can be decomposed as a map of the presence or absence of really simple motifs, like those oriented edges. And there's combinations of those can be assembled to detect slightly more complex motifs. And then combinations of those can be assembled to detect even more complex motifs. And that's kind of the notion of compositionality. There is a saying from a colleague called Jason Eisner at Johns Hopkins University who says, it's sort of an interesting comment on a famous quote by Albert Einstein. So Albert Einstein said, "What's the most incomprehensible about the world is that the world is comprehensible." Why is it that we can understand the world? The world is so complex that there's no way to really understand it. And Jason Eisner's version of it is the world is compositional, or there is a God. If the world really was not compositional, then there would be no way of understanding it, and that means we need superpowers to be able to interpret the world. So we've seen an inflation of the number of layers over the last few years that are used in kind of standard convolutional nets. So a few years ago, the typical convolutional nets would have 20 layers. Google came up with this architecture called GoogleNet, which is a play on the word of GoNet, the original convolutional net that I was using at Bell Labs, that has a very large number of layers. And more recently, Yann, who at the time was at Microsoft Research Asia here in Beijing, invented what's called ResNet, residual networks. He now works at Facebook in Menlo Park. And he came up with this idea that every layer should basically have one of those bypass connections, so that if a pair of layers here fails somehow, fails to learn, then that layer becomes transparent and essentially becomes the identity function. So that allowed to kind of multiply the number of layers to something like 50 or 100 and get systems that work really well, even though they're very, very deep. I was very surprised by this result. I found that was a very interesting idea. So there's been a lot of success in deep learning, and I'm sure some of you have been with some of those ideas. One of the early applications of deep learning at Facebook was to do face recognition, essentially. And this is one of the applications that I would have never thought would work really well with convolutional nets. I thought convolutional nets were really appropriate for sort of category level object recognition, not really for things like face recognition. It turns out it works really well for that as well. That was a surprise. Even I didn't believe that it would work so well. One of the things that we worked on very early on was the idea of applying a convolutional net convolutionally over an entire image so as to label every pixel in the image with a category. In this case, it's a category that indicates whether a particular area is traversable by a robot or not. And then we can use this to drive a mobile robot around. An interesting characteristic of this particular work is that the convolutional net is actually self-trained, so the labels are collected using stereo vision, not using manual labeling. And so it trains itself in the lab, and then it fine-tunes itself while it's running in nature. And so that's an example of this robot running around with the student annoying this poor robot. He's being very frustrated because he can't go control. So this is the student you saw on the left here. This is Raya Hatzel. She was a PhD student with me until 2009, and she's now head of the robotics group at DeepMind. The other student is Pierre Samanet, who is also working in robotics at Google. So a couple of years later, we started working on a similar idea, but where we would classify every window in an image with a category of the object it belongs to. This is called semantic segmentation. And of course, we had the idea at the time that this could be applied to self-driving cars. This was before the self-driving car craze. We're talking about 2010, 2009. And so we never got to work on self-driving car, but the idea kind of kept circulating. And you see self-driving car systems now, particularly the system from Mobileye and from NVIDIA, that essentially use semantic segmentation as a way of labeling the image into traversable areas and obstacles. And there's a lot of work on this at Baidu as well, at various companies in China, in the US, in Europe. NVIDIA has become very, very active in this area. Maybe talk about some more recent work that some of my colleagues have been doing at Facebook AI Research. This is some work from a couple of years ago called SharpMask, or DeepMask, where the system is trained not just to recognize the central object in the image, but also to produce a mask of the object. So if it is, let's say, a zebra, it's going to produce a mask of the zebra as well as a category for zebra in parallel. And this was put in a fairly complex system called Sharkmask++. The code for this is open source. You can actually download it from GitHub. It's called LeCun-Deep. And it's a fairly complex system, but it allows, it ends up producing really good results where you have things like this, where the outline of essentially every object of categories that he knows about are outlined: the cell phone, the person, the laptop, all the people here, except this guy. You see another example. Watch those two things. Those are obviously people, and they are actually labeled as people. You can pick out broccolis in Chinese dishes, at least the American style of Chinese dish. And you can also count sheep. And then more recently, LeCun-Deep and a collaborator at Facebook came up with some sort of very simple, conceptually simple combination of this idea of computing a mask and identifying an object for every location on the input, and built a system called mask RCNN. And so it's basically a giant convolutional net, which for each window or region of interest essentially produces an outline of the object, a mask of the object, a bounding box, and a category. And in some cases even produces kind of a pose estimation for human bodies. And results are absolutely stunning. It works at 5 frames per second on the single GPU. And it produces things like this. So, umbrella, the backpack, the person, the cars are individually identified, all the glasses, the silverware, the plates, the chairs, everything is identified, even if the objects overlap. So this is called instance segmentation, not just semantic segmentation. And this is beating some results on the standard data set. The paper for this just appeared yesterday. So it's on archive. It's this reference here, 1703.06870. You're welcome to look at it. And it can be used also for body pose estimation, and the results are, again, quite impressive. And this one's at 5 frames per second on the standard GPU. Okay, so this was the state of the art. We're about halfway. Now I'm going to talk about obstacles to AI. So, the main obstacles to progress in AI, in my opinion, is the ability to predict. So, you can think of the architecture of an AI system as necessitating 3 essential components, or maybe 4 components. One is perception. Another one is prediction. So basically being able to predict what's going to happen in the world, either because the world is evolving or as a consequence of the actions of the intelligent agent. And that, to be able to plan a sequence of action to get a particular result, the machine has to be able to reason and plan, and basically have memory. So we need perception, predictive models, memory, and reasoning and planning. And I've talked about perception, but not much about the rest, and that's what I'm going to talk about next. Before that, one of the biggest challenges of AI is to build machines that has common sense. What does it mean to have common sense? So, an example of this, which is a classical example in AI, is what's called a Winograd schema. So Winograd is a famous pioneer in AI research, and he came up with sentences of this type: the trophy doesn't fit in the suitcase because it's too large, or the trophy doesn't fit in the suitcase because it's too small. So in the first case, the it refers to the trophy. In the second case, the it refers to the suitcase. And the reason we can lift the ambiguity as to which object the pronoun refers to is because you know how the world works. You have basic knowledge about the world, that a trophy should fit in the suitcase, and carrying it in the suitcase and things like that. If you don't have this basic knowledge about the world, you're not able to lift this ambiguity. Here is another example of common sense. If I say, Tom picked up his bag and left the room, you don't need to know anything about Tom or about the room. You can infer that Tom probably has to stand up, extend his arm, close his hand around the bag, then it's probably going to walk. It's probably not going to dematerialize like this guy. He's not going to fly. He's going to have to walk towards the door. He's going to have to open the door. And all of this you know because you know how the world works. You have some experience of the constraints of the real world. And that's what allows you to fill in the blanks, basically to fill in all the missing information that is not mentioned in this very short sentence. And that's what we call common sense, to some extent. So how do we get machines to acquire common sense? So common sense is the ability to fill in the blanks. And that means you infer the state of the world from partial perceptual information, you infer the future from the past and present, you infer the past events from present state, filling in the visual fields in the retinal blind spot, which we do without thinking, filling in complement in open images. You may only see my right profile, but you can pretty much figure out what my left profile looks like because you know that most human faces are more or less symmetric. Predicting the consequences of our actions and predicting sequences of actions leading to a particular result. So that's what machines need to be able to do to acquire common sense. And they need to be able to do this by being exposed to lots of examples of how the world works, essentially. So there's a big argument for basically what we could call predictive learning, or what others have called unsupervised learning. I think of predictive learning as a special case of unsupervised learning. There's a big argument that Jeff Hinton and others have made for unsupervised learning for many years, many decades in fact. The argument goes like this: the brain may have about 10 to the 14 synapses, and we only live for about 10 to the 9 seconds, so we have a lot more parameters and data. This motivates the idea that we must do a lot of unsupervised learning since the perceptual input, including proprioception, is the only place where we can get 10 to the 5 dimension constraints per second. So, in other words, if we ask a machine to just predict the name of an object, we're not asking it to predict enough information for it to learn enough background knowledge about the world. We have to let it basically learn much more massive amounts of facts about the world by observing how the world works and then training itself to predict what's going to happen next. So that led me to a slightly obnoxious slide that has become a bit of a joke now in the machine learning community, where I say if intelligence is akin to a cake, if you want, the bulk of the cake, the génoise, as we say in French, is unsupervised learning. That's where most of the learning takes place. Most of human and animal learning is unsupervised. The icing on the cake is supervised learning, and the cherry on the cake is reinforcement learning. So there is those three types of learning, and each of these has a different amount of information that is provided to it for learning. So reinforcement learning, pure reinforcement learning, in pure reinforcement learning, a very small amount of information is given to the system at every trial. Basically just a scalar that indicates whether the answer produced was correct or not, sometimes with a delay. So it's a very small amount of information that the system, there's absolutely no way the system can learn anything complex without showing millions and millions of samples. So Professor Yann was mentioning the success of AlphaGo. AlphaGo is a big success of reinforcement learning, and the reason it works is because it's a game, and you can have the machine play millions of games against itself and fine-tune itself. Supervised learning, you're providing a little more information to the machine at every trial, but it's still not enough because all of it has to be supplied by humans. And supervised learning, you're just observing the world, and the machine has a much better chance of actually absorbing a lot more data and being asked to predict a lot more information. So this is a slightly upsetting picture to people working with reinforcement learning, but this doesn't mean I don't like reinforcement learning. In fact, there's a lot of work, very good work on reinforcement learning at Facebook. One of them actually by Yann, who's sitting right here on game playing. So Yann, his collaborators worked on this Doom playing bot that is trained with reinforcement learning. He actually won the competition this past year between various bots to play Doom. Another example where we use reinforcement learning is for strategy games or real-time strategy games like StarCraft. So we have a team effort, in fact several different efforts to figure out how to build intelligent systems to play games of this style that include kind of short-term tactics and long-term planning as well. Strategy. So this is a very challenging problem. This may be the next challenge after playing Go. But really, what I'm advocating for here is not is what is called in certain circles model-based reinforcement learning, which is a very old idea proposed by Rich Sutton back in 1991 in an architecture called Dyna. And so he says the main idea of Dyna is the old common sense idea that planning is trying things in your head using an internal model of the world. And this suggests the existence of a more primitive process for trying things not in your head, but through direct interaction with the world. Reinforcement learning is the name we use for this more primitive direct kind of training. And Dyna is the extension of reinforcement learning to include the learned world model. So this idea of learning a world model, a predictive world model, to help learn a task is an old idea. In fact, it's a very classical way of doing multiple control and reinforcement learning. And that is what I think is the future of intelligent system, or at least one of the techniques for intelligent systems. So in optimal control theory, you have what's called a plan simulator, so a simulator of the system you want to control, and then some objective function you want to minimize. And then you can, through gradient descent or some other technique, you can figure out a sequence of commands that will optimize this objective function, assuming that your simulator is accurate. Okay, that's basically model-based planning for robotics and control. And the idea of model-based reinforcement learning is that you also train, you train this as part of your system, and you also train the system to predict what the sequence of commands should be. So what is the architecture of an intelligent system? A complete intelligent system would be composed of this blue box here. It's composed of three components. So it interacts with the world by sending actions to the world, and then the world responds by using percepts or observations, which go to the perceptual module that basically estimates the state of the world and tells the agent, here is the state of the world. What the agent needs to do now is plan an action so that the action will take the world to a desired state in such a way that the agent in the future is going to be placed in a state that makes it happy. So the objective here is something that tells the agent whether it's happy or not happy. And by minimizing this objective, the agent makes itself happy. Okay? The brains of animals is very much on this, built on this model. So the next question is, what should we put inside of this agent? And essentially what I'm advocating here is the fact that this agent should itself have a predictive model of the world that allows it to predict what's going to happen in the world as a consequence of its actions, or because the world is just evolving itself. And then an actor that generates action proposals that kind of test what the result of the world is going to be of a particular sequence of actions. And what this actor is doing is producing action proposals that will optimize the predicted cost. So this is not exactly the value produced by this objective, but this is sort of a predicted future value, if you want, of this objective. So what you want is the system to kind of make sure it puts itself in a state that will make it maximally happy. And so you can think of all of those as sort of complex recurrent neural net, if you want, which we can unfold in time. What we arrive at is a system that has a perception that is an estimate of the state of the world, and the world simulator that the system can use to kind of plan ahead. And then the actor that generates action proposals so as to minimize the objective function. And if all of those modules are differentiable, then you can backpropagate gradient through all of this and train the actor and the world simulator will simultaneously do the right thing. So we pretty much know how to build this and that, although there's complications in building this. What we don't know really is how to build a world simulator. It's very complex for a system to be able to learn how the world is going to evolve. So how do we build predictive models of the world? There is a number of different ways you can go about this. One work that was done by some of our colleagues at Facebook Research Adam Neros and Lewis and Will Fergus a couple of years ago, we're going to have to do also, was to train a convolutional net to predict what's going to happen in a kind of simulated world, which is sort of a 3D game engine, if you want, a physics engine. And so it's trying to predict where those blocks are going to fall, whether they're going to fall and where they're going to fall. And the system can be trained in background, essentially just supervised by running the simulation in the simulator, and then you train it to produce maps for each of the objects and kind of predict how things are going to evolve. They can make predictions, but they're kind of fuzzy because sometimes it's very hard to predict exactly what's going to happen. It turns out to work okay in real situations. You get those kind of fuzzy predictions. It's because the system really cannot predict exactly what's going to happen. So it kind of makes some sort of average prediction. Here's another example where we're sort of inferring the state of the world from text. So very often when people tell you a story, what you keep in your mind is some sort of estimate of the state of the world as a result of every event in the story. And we wanted to build a system that was capable of doing this. So we used what's called a memory augmented neural net. So this is sort of a new set of ideas that consist in building a recurrent neural net, so a neural net with loops in it, so which is basically a dynamical system, and have the system interact with what amounts to associative memory, very much like a RAM or associative memory. And I'm going to go into the details of how those memories are built, partly because I want to talk about the entity network. So here is what this entity network looks like. So basically, it's a bank of memory cells, if you want, each of which is associated with a little recurrent neural net. And all of those memory cells observe an input, which is essentially a sentence that describes an event, like something like John goes to the kitchen, for example. That sentence is encoded into a vector using an embedding technique, basically a neural net that encodes the words into vectors and then encodes the sentence into vectors. Those vectors are fed to each of those memory cells. And the memory cells have a circuitry inside that decides whether they should be activated and updated or not. So the idea is that you would have a cell for John and a cell for the kitchen. And then when you say John goes to the kitchen, the cell for John gets updated, and so that its location is now updated with kitchen. And the cell for kitchen gets updated, now the content of the room is updated with John. So it's called entity neural net. For that reason, you would imagine that the system will basically use a separate cell in this network for each of the entities in the story, and then the system will learn to update them. So the way the system is trained is that you tell it a story, you run the neural net for the entire story, and then at the end you ask the system a question: is John in the kitchen? Or who is in the kitchen? How many people are in the kitchen? And then you give the answer. And then you train the whole thing with backpropagation. Okay, so the system doesn't know the question is going to be asked until the end. And magically, it works really well. And the system can answer all kinds of different types of questions. In fact, there is a benchmark called the Baby Task that was put together by my colleagues at Facebook, Jason Weston and his collaborators. And they came up with a series of 20 types of different types of questions that you might want to ask a machine after the machine has been fed the story about that. And Entity Network is the first system that actually can solve all 20 of the Baby tasks. So it can do things like, let's see, let me go back to an example. So here's an example. Brian is a lion, Julius is a lion, Julius is white, down on the screen, what color is Brian? So if you assume all lions are white, then Brian is white. Mary joined into the bed, Mary went back to the kitchen, John joined into the bedroom, Mary started with milk, what is the milk before the bed, etc. So there are questions of this type that, each of the 20 different styles of questions if you want. And Entity Network is the first one that can solve it. Okay, now let me switch gear and talk about unsupervised learning. So, as I said previously, one of the main issues in AI is to get a machine to learn one of those predictive forward models of the world. And the main issue with with learning predictive models of the world is that the world is essentially unpredictable. There's a lot of different things that can happen in the world, from a number of different options, and you may not be able to predict which one is actually going to occur. So here's an example where your world consists of 2 pixels. Okay, you only have your 2 eyes with 1 pixel each, and everything you observe in the world is a point in that 2-dimensional space. One of those points. There's obviously a relationship, a dependency between y1 and y2. If I give you the value of y1, there's a good chance you can predict some range for the value of y2. And vice versa, for any value of y2, there might be 2 values of y1 that are possible. So unsupervised learning is really learning those dependencies. And what unsupervised learning consists in doing in one formulation is to run a contrast function. Let's call it an energy function that tells you the difference between whether you are on the manifold data or outside. So here's an example. These are our data points. You'd like to run a contrast function that tells you whether you are on this surface or outside of it, and this contrast function should take low values on the manifold and higher values outside. Those 2 energy functions are both perfectly fine for this particular problem. So we'd like the learning algorithm to basically shape this contrast function, this energy function, in such a way that it takes low values here and eventually gets trained to kind of give higher values everywhere else. And it's not obvious how you do this. People have been struggling for this question and formulated in different ways for decades, in fact. It's not easy to do in high-dimensional spaces. Imagine that this is not a 2-pixel image, but a 1 million pixel image. That's very difficult. So I kind of made a list of about 7 different methods to do this, to ensure that you could learn a contrast function that takes low values on data points and higher values everywhere else. And I'm not going to go through the list, because first of all it will take too long, but also because there is an 8th method that I think is much more promising called adversarial training. So let me speak to this right away. So adversarial training is a new idea, which I wish I invented, but I didn't. It was proposed by Yann, who was a PhD student, at the time, with Yoshio at the University of Montreal. He proposed this idea about 2.5 years ago. And before I explain exactly what adversarial training is, let me try to explain what problem it attempts to solve. So it basically, here's the problem. Let's say you want to train a system to predict the future, and the entire world of the system, all that it sees, is video segments of someone putting a pen on the table and letting the pen go, right? So every time you do the experiment, the pen is going to fall into a different direction. And so the problem that we're to solve here is to train a predictor. So imagine that this predictor observes the past. Okay, so it observes all the frames of the person putting the pen on the table. And then we stop the video and we ask the system, what is the world going to look like half a second from now? So half a second later, the pen will have fallen. And the system has to predict in which direction the pen has fallen. And really, the set of possible outcomes is kind of an entire manifold of possibilities, right? Basically, the pen can be in any orientation. And so, it may be that the system, at this particular time, decides to predict this point, that the pen is going to fall to the back and to the left. But in fact, when we run the video actually indicates that the pen fell to the back and the right, which is another point of this manifold. So what we like to be able to tell the system is that, okay, you were technically wrong because the prediction is not exactly what the video indicated. But in fact, you were conceptually right because qualitatively you were right because you predicted that the pen would fall, and there was no way you could predict in which direction it was going to fall. So as long as your prediction was on this manifold of possibilities, we're not going to punish you. Okay? So that's basically prediction under uncertainty. You want an objective function that tells the machine there is no single correct answer, there's a whole set of possible correct answers, and as long as you produce one of them, we're not going to punish you. Now the problem is, we have no idea what this surface is. And so what we're going to do is, we're going to train a second neural net to tell us whether we are on this manifold or not. And that connects with what I was talking about earlier, about learning a contrast function that indicates whether we are on a manifold of data or outside. Okay? This other neural net that tells us we are on this manifold of plausible futures is going to be one of those energy functions. And that's the idea of adversarial training. So basically, you show the past to the machine, and you run the future of the video from the data set, and that's the actual future. Okay, so that's the initial segment, and that's what actually happens in the video. And then you train this discriminator function, which is the energy function, to give you small values for the blue points, and the blue points are the ones that are coming out of the data set. Okay, so the output of the discriminator is a single scalar, so it's the height of this function. The input is an image, as well as the past. It looks at the past just like the previous module. And it trains itself to produce low values for everything that comes from the data set, which are those blue points. Simultaneously, you have a generator. So this is the module that's going to predict the future. That generator also looks at the past and is trying to predict the future. And initially it does a really bad job. Okay, so the prediction is horrible. And the discriminator is going to take this prediction and is going to try to train itself to produce higher values for whatever it is that this generator produces. So those are the green points. The green points are going to be such that the energy is going to be pushed up wherever there is a green point. Okay. And so after a while, the energy of the green points is going to go up. But simultaneously, the generator is going to train itself to minimize, to produce outputs that make the output of the discriminator as small as possible. Essentially, it's going to try to make the green point as close as possible to the blue points. Okay? So there's two processes here, two simultaneous learning taking place. The discriminator, which learns this contrast function, basically training itself to tell the difference between what really happens and what the predictor produces, the generator produces. And then the generator tries to fool the discriminator into thinking that what it predicts actually comes from the real world. So after training, you get this nice contrast function, and the generator produces green points that are near the blue points. That's the basic idea of adversarial training. There's several formulations of it, and there is new variations of it that pop up on arXiv every few days. It's a very active topic of research. Now, it's very interesting because it breaks the traditional paradigm of machine learning where, since the 50s and 60s, all of machine learning basically, or statistical machine learning, is based on minimizing some sort of loss function. Here, we're not minimizing a loss function. We are actually minimizing two loss functions, and they play against each other. And so that actually is more like a game theory type Nash equilibrium. I'll come back to that in a minute. So those techniques have been extremely successful at generating images. So one thing I didn't mention is that to be able to generate multiple points on this manifold, we need a source of random vectors, essentially. So the generator takes a source of random vectors, and those are used to essentially produce points that are at different places on this set of plausible features. So this example is, these images are the result of training a generator using adversarial training on images of bedrooms, and then plugging a bunch of random numbers, 100 random numbers or so, into the network, and then asking it to produce an image. So those are nice-looking bedrooms that actually don't exist. They are just produced by the generator. This is work that really opened the eyes of a lot of people on adversarial training by Radford, Yann, and Chita. Sonia Chita is a research engineer at Facebook in New York. People have trained this on various things, like manga characters. You can interpolate continuously between manga characters. And every one of them is kind of a decent-looking manga character. Only a few of them are actually real. All the ones are interpolation using adversarial training. You can do amazing things like arithmetics in this Z-space, where if you take a vector that generates an image of a man with glasses, which you can infer, so you show the image of a person with glasses and figure out what Z vector will produce that image. And then you do the same for a man without glasses, and then the same for a woman without glasses. You do this vector, minus that vector, plus that vector, and then you reconstruct the image. You get an image of a woman with glasses. So it's kind of amazing that the system sort of automatically sort of learned sort of relationships and compositionality in the space. This is a bit of the holy grail of pattern recognition, the fact that you can parameterize a very high-dimensional surface in a high-dimensional space, very high-dimensional space, like the manifold of natural images, or the manifold of faces, or the manifold of bedrooms. I use manifold in a loose sense here, they're not actual manifolds. There's a formulation of generative adversarial networks I do with my students, Jake Zhao and Michael Mathieu, which is called energy-based GAN. So it's basically the formulation I mentioned earlier with this contrast function. And what Michael and Jake have shown is that it's basically kind of a Nash equilibrium type of situation where you are minimizing two functions. One function you're minimizing with respect to the discriminator, the other one with respect to the generator. And when you're minimizing one of the functions, it makes the other one larger, so you're just kind of trying to find a Nash equilibrium between the two things. And what Michael and Jake proved is that there is a Nash equilibrium, and if it's reached, then the distributions produced by the data and the generator are equal. This led Jake to actually produce a very interesting system. So it's basically it's a fully connected network that is built as an autoencoder. This is called a ladder network. And by training it with a combination of unsupervised learning and supervised learning using this EBGAN framework, he managed to get 0.9% error on NDIS using only 1,000 training samples. And this is kind of a record. So NDIS is kind of a toy problem, but this is a very small number of training samples and very good performance. So this is an example where unsupervised learning actually helps in doing some results. These are examples of natural images produced with this energy-based GAN framework after it's been trained on the full ImageNet dataset. And you put random vector in, and it produces an image. If you're at the back of the room, you might think these are nice-looking images. If you're at the front, you kind of open your eyes and try to figure out what this is, right? And you can't actually identify any of those objects. They look natural, but they're not actually objects. So what is this? It's like the front of a train. It's got a sail, some sort of wing, it's about water. It makes no sense. So the local structure of those images is correct, but the global structure is kind of wrong. So the GAN systems haven't really captured the global structure. Here's a better example where this is trained on dogs. So these are weird dogs produced by one of those energy-based GANs. And they kind of look like dogs, but they are those kind of soft dogs, right? You know, the Salvador Dali paintings with the soft tops. That looks a bit like Salvador Dali dogs. Another series of work is with video prediction. So this is the problem I mentioned earlier, where we trained what's called a multi-scale conditional net to predict a few frames of a video from 4 frames observed in the past. And if you train without adversarial training, so you just train with D-square to train this architecture to predict the next frames, you get this kind of blurry result. So again, the first 4 frames are observed, and the last 2 frames are predicted. The predicted frames are very blurry. But if you use this adversarial training idea, you get pretty nice predictions where the basketball player continues, the string kind of moves properly, the bow here moves properly, everything kind of continues. Except you can't really predict long term. Here's some more examples. So this is examples where we train a system to predict the video when we train the system on videos gathered in apartments in New York, and then we turn the camera. So what the system has to do is predict what the apartment looks like in areas it hasn't seen before, right? So here is, for example, one where there is a bookcase, and initially it observes the bookcase, and then it predicts what the bookcase looks like afterwards. Same here, bookcase, and then it predicts what the bookcase looks like afterwards. Here it used to predict what the couch is going to look like as the camera pans. It's never seen this couch before. So it's captured a little bit of the structure of the world. But again, it only works up to about 5 frames. If you try to predict longer, after 50 frames or so, after 10 frames, things start to get really bad and early and doesn't work really. So one of the things that we've done very recently, this is very new results, is not predict do video prediction in pixel space, but do video prediction in the space of semantic segmentation. So basically, you take an image, you run a semantic segmentation algorithm on it that indicates the mask of the object, essentially, with the category. And then in that space, you're trying to do prediction. And that actually works pretty well. You can predict up to about half a second or so. You have to use some tricks like train the system to predict recursively by being fed its own input, its own predictions. But it kind of works. So here's an example. Again, the predictions are indicated by the red frame. Okay, so that's observed, and the red frame indicates predictions. So it predicts that the car on which the camera is placed has to go forward, so everything has to get bigger. And then this car has, keeps moving to the left. This one too. It predicts that those pedestrians kind of keep moving to the right. That this car is going to overtake that other car, etc. So it's a very kind of easy way of getting simple predictions of where things are moving. And this, you would imagine this would be very useful for a self-driving car to be able to predict in advance where other cars are going to go, and not just be reactive, but sort of be able to predict in advance what's going to happen. As I said, the ability to predict is the essence of intelligence. Okay, I'm out of time, so I'm going to stop here, and thank you very much for your attention, and take a number of questions. And I think there's a very bright future for AI. Again, I think the main point of my talk is that what a lot of us should be working on is reasoning, planning, and forward prediction. And adversarial training, I think, is a very exciting field that a lot of us are really excited about. Thank you very much.
Thank you, Professor. I'm a junior student in Tsinghua University, and nowadays we are using adversarial network to generate music. And my question is, what's the difficulty and also the potential development of adversarial network? And can the generator create something fancy and more better than human beings? And also, can we create something like art? The performance is better than human. Thank you.
Right, so yeah, good for you first, congratulations. This is a very good topic to work on. I think a lot of people are kind of asking themselves, what does that mean for human creativity? Are we going to be able to build machines that have some creative sense? And the indication is perhaps yes. And that's kind of an new exciting thing. We've seen examples, with very interesting work coming out of Yoshihiko's group at Berkeley, for example, of transforming line drawings into full color images, or inferring, again, so generating full color images from kind of semantic segmentation type images of this type. So those are really nice, and to some extent they paint better than humans, right? They generate images that are nicer than what the humans could paint. There is interesting work, of course, that has become very famous on style transfer, coming out of a group in Germany, where you kind of take the image of a photo, for example, and then you take a painting. And there's a way to kind of manipulate the photo so as to make it take the style of the painting. Right? And it's essentially a convolutional net that, with some sort of operation, you can make the photo take the same statistics as the painting, and basically it looks like the painting, but you retains the main object of the photo. There's a very fast version of it that was proposed by Justin Johnson, who is a student at Stanford, and then some very cool work at Facebook, the Applied Machine Learning Group and Facebook AI Research that actually allows you to do real-time style transfer on the phone. It works in real time. So in the space of just a few months, you went from a technique that took several minutes on a full-scale computer to something that runs in real time on the phone. Of course, it's not the same quality, but it's pretty amazing. So yeah, I mean, I think the question of computer creativity is really an interesting one. Yann's up here, perhaps a good opportunity to look into this. Good luck with your project.
The girl from there. Yes.
Hi, Professor. Thank you for your lecture. I'm from Tencent, one of the largest IT company in China and almost the top 5 company in the world in terms of market value. So our dean just now also mentioned the AlphaGo. So exactly last weekend, Fine Art, which is a AI Go, playing a board game, just won the championship in Japan in the UEC game. And also defeated Japan's famous Deep Go and also France's famous Crazy Stone. But this team, this product, Fine Art, was developed within 1 year in our company with a team with an average age of 27, pretty young researchers and developers. So I would like to ask if you think there will be chances that tech giants from China will soon compete with those in Silicon Valley, or if there is not such competition, can you make some comparison between the East and the West? Thank you.
Okay. So I think there is something very exciting that has been happening in the context of deep learning particularly, but more generally in science, which is that it's becoming a very small world. The boundaries between countries are being erased, essentially. It's always been the case that the research community was really an international community, but now it's as if the world has shrunk. And the reason is because it's become very common for people to publish their results very quickly on arXiv, which makes them immediately available to the entire world community. And you don't need to subscribe to an expensive journal. You can be a student with a 5-year-old computer and still be part of the community because you have access to the same information as everybody else at the same time. Another practice that has become very common is to distribute code in open source. So for example, Yann, who is here, Yann from Facebook, has distributed in open source his Go player, Dark Forest, which is used a lot as a basis of several Go players now. And the AlphaGo is not open source, but the basic principles behind it were published in a Nature paper and various other papers that DeepMind has put out. And it uses basic components that all of us are familiar with, convolutional nets, MCTS, which has been around for a long time, invented by this French team you were talking about, and reinforcement learning, which DeepMind is really an expert. It's a bit of their trademark. And so the combination of those, the fact whenever someone or some team shows that a particular problem is solvable, immediately within a few months you have 4 or 5 teams across the world coming up with either a reproduction of the results or different ways of solving the same problem, because now we realize it's solvable, so there must be multiple solutions. So I think the example you cite is a very good one that indicates how much the community now is communicating so fast. And I think the reason why the field of AI is progressing so fast is because of this emphasis on quick communication. So one of the things that we have emphasized at FAIR from the start is the fact that we do open research. So all the research we do is published. Most of the code that we write is released in open source. And the reason we want to do this is because we want to accelerate progress in the field. Our company, of course, can take advantage of any new technology where it occurs. And so our interest is for the entire field to progress as fast as possible. And it doesn't matter if we are the inventors or not. Of course, we kind of drive the things that we're interested in. So I think it's wonderful that those results are being reproduced. So I think that gives a chance to anyone in any country to make significant contributions. And you see contributions from, there's a paper at ICLEAR this year, ICLR, the International Conference on Learning Representation, which is kind of a deep learning conference. This paper by an undergrad who just worked by himself and had a cool idea about Yann and wrote a paper, submitted it to ICLEAR, and it's an awesome paper. I mean, I think those stories are going to appear more and more. So, yeah, I mean, it's an encouragement for everybody here. Don't have any inferiority complex, just work on what you think is great.
Let's take. Let's take a question from this side. Yes.
Thank you, Professor, for your interesting presentation. So I have a question. In your opinion, what is the most exciting application of AI? And how would you apply it on Facebook, and how will it revolutionize the entire platform? Thank you.
Yeah, I get the question a lot. So there are a few applications that we know are going to change the world, change people's everyday life, right? So self-driving cars, certainly transportation in general is going to change completely because of AI. It will enable self-driving cars, maybe flying quadcopters or autonomous or whatever. And that's going to completely change society because it may change the way people can relate with consumer products like cars. People may not need to buy cars anymore because you can get one from your smartphone at any time for cheaper. So it will change a lot of manufacturing industry. It will automate a lot of the manufacturing everywhere. So I think manufacturing is going to be much more local because robots will be basically building things a lot more than they currently are. And it's already the case that they are building things. So this is going to transform industry. It's going to transform industry in China very much because China in the last few years has built itself using kind of manufacturing in a big way. There is big changes that are going to happen as a result in the design of cities. If people don't own cars anymore, then you don't need to design cities in the same ways that they're currently designed. It's going to change medicine and healthcare. So that's going to be a huge impact of AI in the next decade or so, where there's going to be a lot more personalized medicine, a lot more diagnosis diagnostic tools that are going to use image analysis, for example. There's a lot of work in this area in medical imaging using deep learning for tumor detection and various other things. So this is going to transform medicine, certainly. Predictive learning also, temporal time series prediction is going to change the way we can design treatments for chronic diseases like diabetes or others. So that's going to affect people's lives. In fact, it's going to save lives, both on the streets and in the hospitals, essentially. And then there are applications. So the kind of things that Facebook is interested in. Facebook is in the business of connecting people across the world. Enabling people to communicate. So that includes translation, access to information, compression, and all kinds of different things. But more and more, our interaction with each other and our interaction with the digital world is going to be mediated by intelligent systems. So we're going to have personalized virtual assistants that are going to help us with our daily lives. And those virtual assistants will be under our control. It will basically be our substitute, looking for information for us, organizing meetings with our friends, things like that. And the technology for this does not exist yet. We need those machines to have common sense. We need those machines to be able to plan a sequence of actions to kind of solve a problem like reserve a table at a restaurant or performance or something like this, or travel. So that's one of the things that we need those new technologies for, to build intelligent agents. That's something that Facebook is very interested in.
Thanks, excellent talk.